Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're very happy to have Sergio for a second talk on evolutionary stable strategies of random games and the vertices of random polygons.
Okay, and as I told you, Val, I'll try to make this shorter than the previous talks. On the average, would be okay. I don't say anything about tomorrow. We'll see how much you can. Okay, so
sorry.
Yeah, that's fine. You missed the most important part of the talk already. So. Okay. Okay, so this is joint work with Yossi Rinot and Benji Weiss from the Hebrew University. Some of you may know some of them. And okay, let me start immediately with the following problem. Random points. Suppose I have n random points in the plane. Okay? Now just to make it clear, what do I mean by n random points in the plane? So a point has two coordinates, an x and a y coordinate. And let's assume that all these two n coordinates are IID random variables with the same distribution. Okay, think of this as a continuous distribution, finite support or unbounded support, and also symmetric around 0. That also, it's not important, but we'll have for some things. Okay? So that's how I choose n random points in the plane. Let's look at the convex hull of those points. And let's look at how many vertices that convex hull has. Okay? Let's call this Vn. So that's a number of vertices of the convex hull of these n random points. Okay? And now let's look at the number of distributions. So here we have a uniform distribution. I write here the tail, 1 minus f. So f is a cumulative, 1 minus f is the whatever, the tail, right? It's a tail. Yeah. So that's 1 minus x. And this thing means that I'm ignoring all constants, okay? So not here, but in the continuation. Now the number of vertices turn out for the uniform distribution turns out to be something like log n. Okay? Raise a constant, 1/3 or something, I don't remember exactly. But, okay? Now if we take a normal distribution, the tail behaves like e to the minus x squared. I mean 1 over x or something, but that doesn't matter. The number of vertices is something like square root of log n. Okay? Next exponential distribution, log n. Okay? Now I'm going to put a few more distributions. Let's take a Weibull distribution, let's say e to the minus square root of x. Alpha is less than 1, so take say alpha equals a half. So e to the minus square root of x. Okay? Let's take a stable distribution, 1 over x to the power alpha, for some alpha between 0 and 2, let's say. Particular Cauchy distribution, the tail is 1 over x. Now, for those of you who did not read the abstract, anybody read the abstract? Okay. Yes, so you are not allowed to talk. Okay. So for those who did not read the abstract, a quiz. What should be here? Okay, so I gave you 3 data points, log n, e to the minus x squared square root log n, e to the minus x log n. What would be e to the minus square root of x, you think?
Log n to the alpha. Log n to the alpha.
Okay. Any other guess? Okay, so let me give you another data point. 4. The number 4. Okay, now you want to revise what's written here? You want to revise your estimate?
No.
No. Okay, so I'll give you another data point. And I'll give you another data point. Now you want to revise? 4. Okay? Now, the first 2 results, that's it's classic work of Rennie and Solanke, 1963, in German. It's written in German. If, no? I think so, if I remember correctly. Yeah. The exponential is a result of Hague, 1990, and these 4 come from this paper that I'm going to talk about. Okay? Now, in fact, what happens, so you see there is a sharp cut there, and in fact we identify 2 classes of distributions. Okay? And one, we'll call them EF and SE. EF stands for exponential and faster decreasing tails. So since we are looking at the convex hull of n random points, and we are looking at what happens when n increases, yes? So clearly what matters are large values, yes? Those we are looking at extreme points in this direction, that direction, in all directions. So what matters is really the tail of the distribution. That should be quite clear, yes? So the question is, how does the tail behave? What's the behavior of the tail as we go to infinity, okay? So exponential and faster decreasing tails, okay? And the other class will be slower than exponential decreasing tails, okay? So some examples, if we take the tail to be e to the minus x to the alpha for alpha greater equal 1. So for alpha equal 1, it's exponential. For alpha equals 2, approximately normal, yes? Uniform, I mean the tail just drops completely to 0, yes? Logistic and lots of other distributions that you can put there, yes? E to the minus x to the power 17.2 also works, okay? So those will be exponential and faster decreasing tails. And slower than exponentials, it's like e to the minus x to the alpha for alpha less than 1, strictly less than 1. So, for example, Cauchy, Pareto, alpha stable, log normal, what's called regularly varying tails. All those heavy tail distributions, they are there, okay? And I think that at least when I started looking, Googled heavy tail distributions, what you get nowadays is computer science papers. Because you start looking at networks and all those things, I mean, heavy tail distributions appear everywhere in computer science nowadays. So you shouldn't be surprised, right? Have you seen heavy tail distributions? Okay, so just to have a picture in your mind, so if this is the exponential, let's say the green is the exponential tail, then the slower than exponential, so they go down much slower. Okay, so they go down, whereas the exponential and faster, they drop down very quickly. Okay, and exponential is exactly the changing of regime. Okay. Okay. So now let me. Okay, I won't give you the precise. I'll give you. Okay, I'll give you definition which you know. Okay. In fact, I think this.
Just return a minute to the definition of the problem. The distribution of the points, is it spherically symmetric or no?
No, it's not. Sorry, it is spherically symmetric if and only if it's a normal distribution. Yeah. If it's not a normal distribution, it is not spherically symmetric. Okay, now for spherical symmetric, there are additional results and so on. I mean, Renyi and Solanke have more than just what I told you. But, okay, there should be an introduction. I jumped immediately into the problem, but there is an introduction. I don't care about, I care very much. They are very dear to my heart, yes. Vertices, this came out from a problem in game theory that I'm going to get to it later on existence of equilibria and so on, etc., which translated geometrically to this, and then we got to this problem. So for that problem, it's very natural to talk about independent distribution on the x-axis and on the y-axis. It's natural, so that's what we are looking at. Of course, that's not the most general problem. Okay? So that's my excuse for looking at this problem. Yes?
So are you thinking of two-sided distributions when you say 4? Is the
Yes, I think that's why I say symmetric. So the distribution is symmetric, so the minus and plus are the same. Okay? If it's not symmetric, then it's a little more. Again, you can put one tail like this, and on the other side, the tail, here is a heavy tail, here is a light tail, and then you can imagine what's going to happen. Okay, so exponential and faster decreasing tails, that's defined in a very easy way, that the tail is a log concave function, which means that the log of that is concave. Okay, so e to the minus x squared is concave. Okay, or e to the minus x to a power bigger than 1, greater or equal 1, that's exactly log concave function. Okay. On the other hand, the s lower than exponential decreasing tails. Now here I'll give you. In fact, our categorization is wider than what I write here, but I'll put here something a little simpler, and that's 1 minus fx being a log convex function. But that's not sufficient because that still includes the exponential. Exponential is log affine function, log linear function, yes? E to the minus x, the log is x, minus x. Okay? So there is an additional condition which here is a sufficient condition. Of course, you don't understand anything from that, but here is a condition. Let me connect it to something that perhaps you know. There is a family of distributions called sub-exponential distributions. Anybody has met those fellows? No? Okay. Sub-exponential distributions have the following property, that if you take x and y, IID distributed, IID with the distribution f, then the probability that the sum is large, I mean, the sum is large, in fact, essentially if and only if one of them is large. So to get the sum large means that either x is large or y is large. So this is like the probability that x is bigger than t plus the probability that y is bigger than t. They are IID. So the sum is large if one of them is large. Okay? Those are sub-exponential distributions. And again, in the class of heavy tail distributions, those whose tail is heavy. Heavy means they go down slowly. Okay? So those are famous or well-studied distributions since, I don't remember since when, but that rules out exponential. It's strictly sub-exponential. Okay? Now again, our precise definition, if you want, you can look in the paper. It's more precise than that, but that's sufficient to describe it. Okay? So here is now the result.
There are no distributions which are neither low concave.
Oh yes, yes, sure, there are. So can you remember this towards the end? The last slide, I have an answer for you. In fact, I have something to say about that, yes? This doesn't, I mean, there are distributions that are neither, you know, they can go like this, yes, wave around, and I'll say something about that. Okay, so if f is an exponential and faster, so those are those that go down fast, then the number of vertices goes, the expected number of vertices goes to infinity. On the other hand, if it's an SC distribution, if it's lower than exponential, then the number of vertices converges in probability to 4, which means the probability that it is 4 goes to 1 and then goes to infinity. So not just expectation is 4, but it converges in probability to 4.
You're quite embarrassed to have missed the very beginning of your talk, but the number of vertices on the convex hull
yes.
of n vertices.
Right. You take n points in the plane, n random points in the plane. You take the convex hull. You take a distribution on the reals, and you choose n x's and n y's independently. That gives you the n 2n. So you have 2 NIID random variables. Gives you the n points. Take the convex hull and count how many vertices it has. Okay. Now, since I know that people here like pictures, here are some pictures. Okay. That's for uniform distribution. What happens with a uniform distribution of, say, -1 to 1 or something? You're just going to fill the square. However, uniform belongs to the exponential and faster. So how are we going to get lots and lots of extreme points? In the corner. Switch here. I mean, on the faces, on the edges, we are going to get very few. Okay. All the action is in the corners. Here we have lots. Now these are 10,000 points, and we have here 29 vertices. Maple, just I ran Maple. Yes, it's. And you can see that here there is a lot of action. You can easily do 100,000, and you know the point is that all this will become more or less black, and you will see here that that's where all the action happens. So when you turn the corner, there are lots and lots and lots and lots of vertices, and that's how it goes to infinity. Okay, that's a uniform distribution. Okay, normal, very different picture. Okay, but nevertheless, the number of vertices goes to infinity. So these are all the points, and these are the vertices. We have here 16 on 10,000, yes? I don't know if it fits. I mean, anyway, I didn't put down the constants in the square root log n, so you don't know what, okay? Exponential, okay? Notice, okay, changes, okay? This is normal, okay? It still fills a lot. Now this becomes more concentrated. Let's take now y bull with parameter and a half. So it's e to the minus x, e to the minus square root of x. That's how it looks like. You see the 4 points. 1, 2, 3, 4. And all the rest are here. Cauchy. Look at this. Cauchy, all the points are here. There is 1 here, 1 here, 1 here, and 1 here. That's really what happens. So how do we get 4 points? 4 points, I mean, we essentially always have 4 points. Take the thing that is maximal in the, like this. Take the thing that is maximal in the x direction. That's clearly an extreme point. Take the one that is minimal in the x. It's extreme. maximum y, minimum y. So you have 4 points, unless, of course, one of them turns out to be simultaneously maximal in x and maximal in y, which has probability 1 over n just by exchangeability, by symmetry. So that has probability going to 0. So you are going to have 4 vertices with probability converging to 1. The point is that's all you are going to have. Because for those distributions, I'm going to explain this a little more, but for those distributions, for those distributions, the maximum in x is so big, is so large, that really all the others are much, much smaller. You can see here the scale. This is 4,000. This is 6,000. Those are Cauchy with parameter 1. Okay? All the other entries are here, about 100 at most. If you look at Weibull, for example, this is 150, 60, and things are here, concentrating in the middle. But still, it's not. But still, we only get 4. That's what the theorem says. Again, let me show you all the pictures again, so you get so uniform, normal, exponential. You sort of see the beginning of this quadrilateral, but there are a few points in the still goes to infinity. Yes. Okay. But once you go even to e to the minus x divided by log x, that's it. The number of vertices is going to be 4. Okay. That is a real sharp. Okay. Now, okay.
Is it expected that if you take these 4 points, the other coordinate is almost 0?
The what? If what?
You take the 4 points.
Yeah.
Yes.
And the other coordinate of each of these points is almost 0.
Yeah, right. Because again, the property of this heavy tail distributions is that when you take n such random variables, or 2n, doesn't matter, okay, you look at the maximum. The maximum is much, much larger than the second highest. So all the others are much less than the maximum. That's what, I mean, I think that there is even a name for these distributions. Yeah, Benji gave me a paper, outlier prone or something, outlier prone distributions or something. I think, I may be mistaken, but.
The point he was asking was about the y coordinate of the maximum.
Yeah, no, so those are 2n. Again, remember, there are 2n draws from, say, Cauchy distribution. So the maximum x is one coordinate. The corresponding y is just another draw independent from Cauchy. And so since the maximum is much larger than the second highest, is also much larger than everything else. In particular, the y coordinate of that point, for which x is maximal. So that's why the figure that you have here, that those things are very close to 0, that's correct. Yes, because remember, all the other points, look how concentrated they are, yes? All the action is here. Yes, there are a few points here, yes? There are a few points here, okay? But they are very close, yes? If a point is big in one coordinate, well, it happens. But there is no reason to be simultaneously big in both of them. That's a low probability event. Okay. Now, for exponential faster, in fact, there is an easy proof of this result. So I'll show you. It's not that it's important, but I don't know. I don't know why I have it here, in fact. It's, well, okay. Because the other one is so complicated that I can't put it. So I put the easy and uninteresting proof. I'm not sure why. But anyway, so the result of Hague is that for exponential distribution, the expected number of vertices goes to infinity. In fact, he gave the log n bound. Okay? Now, if we take a distribution in the class of exponential and faster, exponential and faster decreasing, so those are tails that drop down fast, yes? Fast tails, yes? Then, in fact, you can always write such a random variable as a convex transformation of an exponential. Okay? A convex transformation of an exponential. Now what happens? So think that you are drawing exponential and then you're applying phi. For example, to go from exponential to normal or something with tail e to the minus x squared, you square all the values. So you have an exponential distribution. And now you want to generate from it something where the tail is not e to the minus x, but e to the minus x squared. Just take the exponential and square it. Okay? Positive and negative separately you do, yes? Okay? So what's going to happen is the following thing. So if you had, for example, this was an edge for the exponential, after transformation, yes, so this was something like this. After transformation, when I take the square, this is going to become something like this. So a point that was here may now be here. So I may get new extreme points, but I never lose extreme points. Okay? What happens is that the thing convexifies in some sense, so I can add extreme points, but I never lose them. Supporting, I mean, just whatever was extreme stays extreme. I told you it's an easy proof, yes? So the number of vertices for a general distribution in the faster than exponential is at least as large as exponential. Okay? So if that goes to infinity, then of course that goes to infinity. I told you, once you understand this, it's a triviality, yes? So
You were going to explain to us Higgs theorem too?
no. It's a complex computation, which also Benji did it independently, and believe me, it takes some, even for Benji, it takes quite some time. Took a few weeks, and no, not a few weeks. I mean, took some time, and it's very carefully estimating this and that and so on. So that's not okay.
So even to show that it goes to infinity, not just
Even to show that, in fact, as I'll show you, at some point we had a very nice proof of something which you still don't know. Which I'll tell you, which we're interested about, which hinged on the fact that the number of vertices goes to infinity. So I remember talking to Benji and saying, oh, so we just need to prove that. In fact, that's quite an easy argument, that as the number of points increases, no matter what the distribution is, you are going to get more and more extreme points. I mean, you can't be stuck at 17. I remember even saying 17, yes? It's one of my random points, 17, So I said, oh, here is a proof. No, that doesn't work. Okay, here's another proof. That didn't work. Until we suddenly realized that we can't prove that. I even remember, we started asking people, okay, here is a nice exercise for you. N random points prove that the number of extreme points goes to infinity, yes? Until we realized that it doesn't. That, in fact, there are distributions for which it doesn't. And that was quite a surprise, yeah? Okay. Now, for SE, let me give you a hint, yes, because as I said, the proof, in fact, is a long, lot of estimations and approximation. I mean, it's not easy, yes. But I'll tell you what the idea is. So the idea is this, that okay. So first of all, sub-exponential distributions, so in particular those in SE, have the following property. So that's a restatement of what I said before, that in order for the sum to be big, one of them must be big. So that means that the probability that the sum is big, larger than t goes to infinity, is approximately like the probability that the maximum is large. So in order for the sum to be large, the maximum has to be large. Okay? And this means, this tilde here means that the ratio of those two probabilities goes to 1 as t goes to infinity. That's a precise statement, okay? So asymptotically, the probability that x plus y is larger than t, which is, of course, we're talking non-negative. It's essentially the same as the probability that the maximum is larger than t. So what's going to happen is the following thing. So the way one proves it is this. One takes here a very large t, okay? And then one takes here, okay, let's look just now at edges. Now, the number of vertices, surprisingly enough, is like the number of edges. So let's count edges instead. Okay, we are in R2, so it's safe. So what I want are edges, okay, that have positive normals. Okay, so what's going to happen is this: in order to get such an edge, what will happen is that one point is going to be here and one point is going to be here. So this thing, this t goes to infinity. The width here will also go to infinity, but relative to t is much smaller. So this width is going to be small o of t. And what small o exactly depends on the distribution. So you're going to have a nice, how do you call it, tube or something there, which goes to infinity. This becomes larger, but relative to where we are, it's very small. And what happens, all the action is going to happen here, which means the probability of having a point here and a point here goes to 0. Okay? For those distributions. You are going to have a point here and a point here, and all the other points are going to be much below this line. Okay? Now, that's the idea, but the proof is more complex. So, read the paper. I mean, that's why we write papers, So somebody hopefully will read them once. And, but that's, That's what happens there. Okay. Right, so 3 dots. Okay, so here I show you the picture again so you can see again exactly how you are going to have. So these are really those tubes where all the action happens. So in a sense, you show that the probability of having something here goes to 1, and the probability of having other things go to 0. You have to estimate things going slower than 1 over that, and so on. I mean, there are lots of estimations. Okay, now that's, as I said, that's a side product. Okay, what we started, is from something else. So my previous talk, I talked about Nash equilibrium and correlated equilibrium. So now I'm going to learn another equilibrium concept in game theory. And that's it, nothing more. Only 3, yes? You don't, I mean, this time. So what happens is that in Jerusalem we have now a Center for Rationality where we have people from lots and lots of areas. We have mathematicians and economists and computer science and biologists and philosophers and lots of interesting people. And now we just started a PhD program in rationality. Okay, we are really going to get rational PhDs. Okay, no square root 2s over there. So I taught there a course with somebody from the statistics department, not Yossi Rinot, Uzi Motro. If you know Uzi Motro, he's a statistician, in fact, also a probabilist. And that was quite fun because, you know, evolutionary game theory and so on. And some of the computer scientists, you know, like Noam Nissan, were sitting there. And then when we came to this notion, which is evolutionary stable strategies, you know, computer scientist immediately says, okay, what happens when n goes to infinity? Yes? That's automatic, I think. It's computer scientists who show a problem and says, what's asymptotic behavior? Okay? So let me describe to you the concept, and then let me tell you what the question was. So let's start with an n by n payoff matrix of a symmetric two-person game. Okay? So what you have is now, what's a symmetric two-person game? So the idea is that there is what's called the one population model. So there is a one population, okay? And they interact. So one individual interacts with another individual in the population, and each individual has a certain strategy. And in a biological world, a strategy is the gene, is dictated by the gene. So there is a gene that tells, you know, when you meet some other guy, go to sleep, or when you meet some other guy, go and fight, when you meet some other guy, go and dance around. I don't know. Each one has a different gene on how to behave when you meet somebody else. And there is a payoff, okay? So when one meets, now it's a one population, so it's asexual. It's a simpler model, yes. No sex yet. Sex comes in the next iteration of the model. Those are two population models. But now the simplest model, there is one population. The standard example is this was introduced, by the way, by Maynard Smith and Price. Those are two biologists in the 70s. Their example was a hawk-dove game, and they showed how you can have a population where a certain proportion plays hawk strategy, a certain proportion plays dove strategy, and the whole thing is in equilibrium. Okay? Because when I play hawk, sometimes I'm going to meet a hawk who is going to fight me hard. Sometimes I'm going to meet the dove who is going to run away. Okay? And the proportions are exactly such that the whole thing is in equilibrium. And that was really a nice concept. And let me tell you what that is. Okay? So what's an evolutionarily stable strategy? Okay? For those that understand Hebrew, I have a beautiful joke, but I won't tell it now, on translation of English terms into Hebrew, which came out quite... so Yuval, ask me at the end. Okay. Then nobody else will understand it. So what's an evolutionary stable strategy?
At least 4.
So in Haaretz, which is intelligent newspaper, let's call it, in a daily newspaper. So in the one day I read in the, they have a back section, science and something on some biologists that are looking at horse strategies. So I said, that's what is this? So I said, I have to ask my biological colleagues, what is this new concept, Now 2 days later, I just flew, so I had The Economist. It turns out this was translated from The Economist. And I look at the same article in The Economist, I suddenly see they are talking about evolutionarily stable strategies. Now, somebody translated stable, horse stable. So it became the horse stable strategy, yes? Okay, so that goes a new concept, you know. Okay, so that's stability, okay? Evolutionarily stable strategy. No, it's a true story, but I can show you it's not, I mean, I could have invented it, but I didn't. I mean, too far out to be invented, yes. No, I mean, the funny thing, I looked at it, you know, I knew about evolution stable strategies, you know, until I saw it in English, only then it dawned on me that that's what happened. Okay, so a mixed strategy. What's a mixed strategy? So we have n different strategies, and the mixed strategy, it's a probability distribution, P1, P2 up to Pn. So P1, it's a probability of playing 1, 2, up to n. Or if you want, instead of probability in the biological model, it's what percentage of the population plays strategy 1, that's P1. What percentage plays strategy 2, that's P2, and so on up to Pn. So it's a probability distribution over the n strategies, or the n genes, whatever you want, okay? So an evolution stable strategy is the following. First of all, it's a symmetric Nash equilibrium. Remember that this is a symmetric game. Okay? So if I play strategy number 1 and Yuval plays strategy number 2 and we meet, the payoff only doesn't depend that I am Sergio and he is Yuval. Depends on what I play and what he plays. So the payoff depends on my strategy and the opponent's strategy. That's all. Not who is player 1 and who is player 2. This has no meaning because it's just one population. Okay? If you want, that corresponds, for the game theorists that are used to think in terms of payoff matrix, the payoff matrix of player 1 is the matrix R, the payoff matrix of player 2 is a transpose of R. Okay? That's what corresponds to all this story. So a symmetric Nash equilibrium means what? That the payoff from playing P against P, oops, I made a mistake. That should be greater or equal than RQP for all Q. I'm sorry, that's wrong. R is the payoff of player 1. So what we have is RPP is greater or equal, so that means that probably all the formulas after that are wrong. Okay, we'll see. Then RQP for all Q. Okay, so if everybody plays P, so that's what the population I'm facing is, for me to play P is as good as anything else. It's the best. So the best reply to P is P itself. Okay? And so that's just a symmetric Nash equilibrium, nothing new. But there is another condition which says that the equilibrium is immune to invasions by rare mutations. Of course, if suddenly a new population comes, 50% that are different, anything goes. But if there is just a small fraction that suddenly plays something different, I want this not to persist. Okay? So what does it say? Here it's written correctly, I see. Okay, so that says the following. Let's go through this. So P is the existing population. Now I have a mutant Q. So the new population is now 1 minus epsilon P plus epsilon Q. Epsilon is small because there are only few mutants. Okay? So that's the new population. Now if I play P against the new population, it's much better, or it's better than if I play Q. So the mutants are going to get a lower payoff than the existing population against the mixture. That means that in the now if you think about the payoff, this R, as being fitness, the number of descendants, for example, some measure of that, that means that the Qs are going to have, on the average, less descendants than the Ps. So the Ps are going to multiply and the Qs are going to die out. Okay? So that means that a Q mutation is not going to survive. Okay? So that should hold for every Q and for small enough epsilon, where epsilon may depend on Q. So for every mutation, there is a certain barrier, epsilon, 0, so that if the proportion of mutants of this type is not bigger than that epsilon, then they are going to be wiped out. Okay? That's additional stability condition that makes this whole thing an evolutionarily stable strategy.
So this assumes that the pairs who play against each other are matched at random.
Yes, that's a random matching model.
Mutation
Right.
develops locally, it might not be true.
Right. So that's why there are models of local mutations. I mean, there is a whole jungle out there, yes, in the positive sense. I mean, there's just the beginning of evolutionary approach. Okay? Now, this condition is not so nice, so here is another way to write it. Here again, sorry, so that's what should be written. So ESS1 is wrong, but ESS2, yes, how could I miss it? Okay, you can restate ESS2, the second condition, the immunity to small mutations, as follows, says the following. If there is some Q different than P, such that against P, it gives exactly the same payoff, then Q against itself is worse than P against Q. So what happens is this. If a mutant comes, and the mutant gets, there is an existing population P, and the mutant Q comes. If the mutant gets less against P, gets less than what P gets against P, then the mutant is wiped out very quickly. But if it has the same payoff, so if it's also best replied to P, then we have to look at second order effects. And the second order effects are that P is going to meet Q versus Q is going to meet Q. And that makes sure, this second order effect makes sure that they are indeed wiped out. If you don't like this, that translates, by the way, into a negative definiteness of the matrix of the best replies to P subject to a side condition. So there is a nice algebraic characterization of those things. Okay? Yes?
Probably a stupid question. If you have a population in which each player themselves is playing a mixed strategy, then is that sort of contained in what you're saying?
Yes and no. In some variants, yes. In some variants, no. In fact, no. So, for example, it's not doesn't have to be immune to say having epsilon over 2, having two invaders, half epsilon playing Q1 and half epsilon playing Q2. That won't work. That can invade. Okay? But if a uniform Q can't invade. Okay? So there are, again, there are refinements and changes and variants. I gave you the main definition. Now, unlike Nash, there are games with no ESS. Finite games, yeah, sure. I'm talking about finite games, not infinite games. So there are finite games that have no ESS. In fact, the simple example is the 3x3 game, variant of the rock, scissors, paper game. Okay? In fact, it's not a pathological phenomenon. Around those counterexamples, there is a whole neighborhood where there is no ESS. Okay? So the question of existence of ESS, the answer is no. You don't. It's not like Nash. Question is, okay, so as I said, games of size 3x3. Now what happens, so here is Noam and Nati, in fact, that asked me. They are now writing an algorithmic game theory encyclopedia or book or something, so they, computing equilibrium and so on, so they asked me, so what happens when n goes to infinity? Does almost every large game have an ESS? Okay? So maybe for 3x3, we have counterexamples, but maybe when the size of the game increases, then there will be an ESS, generically or something. So how do we reply to this? Okay? So let's look at a random game. What's a random game? A random game is just that, remember, a game matrix, we have n square entries. So let's use a MyID. Okay? That's as simple random that I can think of. The simplest possible. It's a random matrix. So those are n square IID random variables, all with the same distribution f. Okay? Now, let S and K, in a moment you'll see why I want to look at that. That's going to be the number of ESS with support of size K. Okay? So those are KSS, or what's called K-allele polymorphisms. Forget that, okay? Of a random game. Okay? Now, pure ESS is an ESS with support 1. That turns out to be a simple answer. In fact, when they asked me the question, in 1 minute I gave that answer, which is trivial and, in fact, well known, that the number of ESS with support 1 is a binomial random variable n and 1 over n. So n, you have n experiments, each one probability of success 1 over n. Okay? Which in the limit, as n goes to infinity, is a Poisson with parameter 1. Okay? So that turns out to be, I mean, for ESS of size 1, the answer turns out to be very simple. You get an ESS of size 1, generic, I mean, for continuous distributions at least. So this is going to be an ESS of size 1 if and only if it's a maximum in the column. And being the maximum in the column has probability 1 over n. The columns are independent, so you get this thing trivially. Okay?
So what do you mean exactly by the support of an ESS?
So what's an ESS? An ESS, okay, thank you. So an ESS is P1, P2, up to Pn, a probability distribution. Okay? So support, so if all these things are 0, that means support of size 2. And those things are positive. Yes? That's a support of the probability of the n-dimensional probability vector. Okay? So pure ESS means that there is just one strategy being played. So for pure ESS, it's simple. And then we asked ourselves, okay, let's go to 2 ESS. Yes, that's the next step. Okay? So here is the theorem. The number of 2 ESS. How many ESS with support of size 2 we get? Now, you already guess. You want to guess? No? Okay. So if it's an EF distribution, the expected number of ESS with support of size 2 goes to infinity. If it's an SE distribution, what happens? You want to guess? Sorry, a half. A half. There is a factor of 8 there. I'll tell you in a moment. So the expected number of ESS of size 2 goes to a half. Okay? In fact, we can say much more. And that's, in fact, more interesting. So let's look first at the SE. Not just that the expectation goes to a half. The distribution goes to Poisson with parameter a half. Okay? So you get a nice Poisson approximation. Those are not independent. I mean, it's not a sum of independent random variables. So for Poisson approximation, one has to use what's called the Chen-Stein method, which I guess some of you know it. So adding dependent random... Sorry?
And Yossi Rinot knows it very well.
Yossi Rinot knows it very well, of course, yes. So adding random variables which have a small probability of being 1 and a large probability of... So they are 0, 1, okay? Small probability of being 1 and independent, that's what gives you Poisson. But even if they are dependent, if the dependence is not too large, you can bound the dependence, then you still get a Poisson approximation. And so much of the work was in getting this. As for the first case, there is also a Poisson approximation, and that is that the distribution of the number of ESS of size 2 and the Poisson with parameter, which is the expectation there, that goes to 0. Okay, so in a sense, that goes to Poisson with parameter infinity, which grows exactly, say, if it's an exponential distribution like log n. Okay, so it's like a Poisson log n, or if it's normal, Poisson square root log n, or whatever. Okay, so you get this nice approximation. Now, surprisingly, the proofs of those two Poisson approximations are completely disjoint. They are completely separate arguments. Yes, the analysis is very different. Each one of them goes by a different kind of approximation and estimating. One has to estimate second moments, yes, and that's what happens. Okay, now what's the connection? So the connection is that the number of vertices and the number of ESS of size 2, there is a factor of 8 between them. That's why 4 became a half. Okay, and let me explain to you where does this come from. Who cares about, I mean, how do you get from ESS to vertices? Okay, so in fact, okay, where's my, okay. So this is my matrix, okay? And suppose I want an ESS that sits here on the first 2 rows, okay? So what I must have is the following property. So there is here a P1 and a P2, and everything else is 0. So that's my, can you see this, or it's behind the, sorry, I should move this a little, right? You can't see it. Okay. Now can you see it? Can you see it? Okay. So that's P1, P2, 0, 0. So I want to know when is this an ESS. So that's an ESS with support of size 2. Okay? So what happens is this. Let me call this x1, x2, x3, xn. y1, y2, y3, yn. So this is what I called R11, R12, and so on. But let's call them x and y's. So the condition is this, that if I look at, now, remember, P1, P2, 0, 0 is the population. So when you play the first strategy, what is your payoff? Your payoff is going to be P1, x1 plus P2, plus P2, y1. Correct? That's a payoff from the first row against the P population. From the second row, you get P1 x2 plus P2 y2. Now, since in equilibrium both of these are played with positive probability, those things must be equal. That's just the equilibrium condition. What happens if you play the third row? You get P1 x3 plus P2 y3. Because it's an equilibrium and you don't play this, it means that the payoff has to be lower. It can't be higher. If the payoff here would be higher, then you'll start playing the third row. That will contradict the equilibrium condition. So this is less than or equal than those things. Generically, in fact, since those things come from a continuous distribution, you know what, let's leave, you can even say strictly less. And the same for all these things. Now you understand, okay? Now, what does this mean? Remember that P1 and P2 are positive, and they add up to 1. So what's the geometry of this condition? So if I draw here this point, which I'll call, say, x1, y1. So I'll put here x, and I'll put here y. And I draw here this point, whose coordinates are x2, y2. And I draw the line joining them. What's the slope? What's the normal of this line? This is exactly P1, P2. That's this equation. And where are all the other points? Below. So this is, for example, x3, y3. They are below this line. So that exactly says that the line connecting those 2 points is an edge. Of what? Of the convex hull of the points. You see the connection now? Okay, so when you translate this, you exactly get the geometry of that problem. Except that what happens in the ESS, we have 2 things. First of all, we need this to be positive. So we need the edge to have positive normal. That's a factor of 4, because I'm ignoring those edges and those edges and those edges. Okay? And there is another factor of 2 that comes from immunity to invasions, which I haven't used yet. The immunity to invasions says that my points must be like this and not the other way around. So if this is x1, y1, and this is x2, y2, that's okay. If I exchange them, which is probability half, then it's no longer an ESS. Okay? You have to believe me about that. So that's a factor of 8. So factor of 4 comes that I want positive direction, and another factor of 2 comes that they must be ordered in this way. Okay? You have to believe me. Trust me on something. Okay? However, and it's very important, that's true only about the first moment. The distributions are different. Only the first moments of those 2 problems are there is this relation, this factor of 8. So the 2 problems are equivalent in terms of expectations only. Second moments, third moments, distributions are different. Okay? The reason they are different is the following. Let me explain to you why they are different. In the vertices problem, we only look at this 2n. There are only 2n random variables relevant, right? So when I'm asking, let me say something, let me backtrack for a moment. If I'm asking, what is the probability that I'm going to get an ESS sitting on the first 2 rows? That's exactly up to this factor of 8, the probability that this is an edge. So probability here, that's like expectation here. But if I start asking, what happens if I'm looking now at an ESS sitting on those 2 rows? Yes, let's say row 4 and 5. Then I no longer look at columns 1 and 2. I look at columns 4 and 5. So that now talks about something completely different. And if I'm interested in, say, 2 and 3, then I'm going to start to have to look at this, say, Z2, Z3. Okay? So for the ESS problem, I have n square random variables that are all independent. And the correlations there are very different than in the problem of the vertices, where I just have 2n random variables. So those problems are different. In terms of probabilities or first moments, they are isomorphic. There is this factor of 8. But that's where the buck stops. Yes, they are no longer the same. Okay.
Don't you also have a factor of n choose 2? Because
yeah, when I go from probability to expectation, there is an n choose 2. But that's in both problems. It's the same factor. Because the probability of being probability that this is an ESS is the probability that this specific edge, that this specific 2 points give me an edge. And I have n choose 2 such edges, so I multiply everything by n choose 2 in both problems. So And there is the 8 factor that makes sure that everything is okay. Okay, now as a corollary, if you remember, for distribution, sorry, mistake. That's not SE, that's EF. What's written on top is correct. Forget that. I see that, yes, I made some changes last night, and that's always a bad thing. Yes, I added some slides, decided that I have to. Okay, the probability that there is an ESS converges to 1. Why? Because of this. Because the distribution of that is Poisson with a parameter going to infinity. Okay? So the probability that I'm going to have an ESS with support of size 2 goes to 1. Okay? On the other hand, if I look at distributions in SE, I don't know what happens. So in fact, oops, I didn't say that. Okay, let's go back here. From this, it follows that the probability of having an ESS of size 2 is 1 minus e to the minus a half, which is something, but it's not 1. Okay? So there is a probability of having no ESS of size 2. Okay? So what do we do? For distributions whose tail goes down very fast, we know that already with size 2, probability of having an ESS is 1. So we have a good answer. Large games whose entries come from a distribution whose tail that goes down fast, they have probability 1 of having an ESS as n goes to infinity. Okay? But what happens here? Here, we looked at ESS with support of size 2. So we go to bigger support. Size 3. So now conjectures. Okay? Conjectures, which means we have some nice, since we understand the geometry and what happens, we have a nice idea of what's going on, but we have no proofs. Okay? So we haven't, I mean, we didn't try even to prove it formally, but I think that those conjectures are quite safe. Okay? I give them a higher than 50% probability that they are correct. Okay?
The extreme points.
So now what happens when I look at SN3, okay, so those are ESS with support of size 3. So now, when I talked about size 2, I was cheating because all the time I talked about vertices. That's not the point there. The point there is edges. The correspondence was, but edges and vertices is the same, so I was counting edges because it was more convenient. Okay? Here now I have to start counting faces. Okay? Because this figure now is going to be in 3 points, and what I need is that the plane through these 3 points is going to have a positive normal, and everything is going to be below. So I have to count faces. Okay? And that's tough. I mean, it's more difficult. Yes? Nevertheless, now if you remember, ESS with support of size 1 was Poisson 1. ESS with support of size 2 was Poisson a half. We conjecture that this is Poisson 1/3. Now it's very important, because if this continues, sorry, I should say one more thing. Turns out that in fact if you, I forgot to say, okay, another result that is proved, forget this, SN1 plus SN2, that converges to Poisson 1.5. So those things are not independent, but nevertheless another change-time application shows you that the dependence is small enough that if you look at the number of ESS of size 1 and 2, you get Poisson 1.5. Like Poisson 1 plus Poisson a half. Our conjecture is that this continues. Namely, the number of ESS with support of size 1, 2, or 3 is Poisson 1 plus a half plus a third. Okay? Next line, Yuval. What's the next line? At this point, we are extremely happy because that means that when this continues, you get a quarter and so on. So it's Poisson with the harmonic series, which diverges, so you get probability 1. Now, our conjecture, in fact, that it stops there. For support of size 4, the immune to invasion condition becomes tougher and tougher, and in fact is going to destroy it. And we conjecture, now this is much, I mean, here I'm betting on whether it's correct or not, I'm going to lower the 25%. I mean, I'm conservative. No, I think, I mean, we have a good intuition why it's indeed no longer converges to Poisson, but rather it converges to 0. Okay? If this is correct, then the total number of ESS converges in distribution to Poisson, what is it? 1 plus a half plus a third. Okay? Which is that probability there is an ESS is only 84%, not 1 for these distributions.
Well, going from 3 to 4, you have some problem there.
Yes. From 3 to 4, what happens? The geometry. Okay, I didn't talk.
Not from from L equals 3 to 4, but from the third bullet to the fourth bullet, even if we believe the third bullet,
Yeah.
that doesn't. It's not clear that the fourth bullet follows.
Of course it's not, because we have more and more terms. I know. That's why I say again, my estimate of those conjectures being correct goes down as I go down the bullets. Okay, so it's I started 50%, 25%, that maybe 10%. I don't know, but the intuition is there. So again, I mean,
But 10% being correct doesn't mean that 90%.
Sorry.
That you think it
It
follows
just tells you how much
90%
money I'm willing to put if you are going to bet on this. That's all. No. That's riskiness. That's another. If you want to hear about riskiness, that's another talk. Okay. So where was I? So what happens is that the second condition of ESS, which for support 2 just says the points have to be this way and not the other way around. Okay, that was a very simple condition, just gave a factor of 2. For 3 was another symmetry, yes? So in fact for 3, by the way, the geometry for 3, if you take a Cauchy distribution or one of those, so you take n random points in space. Look at the convex hull. How many extreme points you have if you have, say, a Cauchy distribution, one of those heavy tails? 7? You want to 6. Exactly. Maximum x, minimum x. Maximum y, minimum y. Maximum z, minimum z. So you are going to get.
How many faces?
Hmm?
How many faces?
No, when you look, so in a sense, what you're going to have that the extreme points are going to be very large in one coordinate and very small in the other coordinates. Exactly like who asked about it? Yossi, you asked exactly. So it's going to be something like very large M00 or 0M0. Now, if these are the points, the geometry, then when you look at such points and you take now the face given by M00, 0M0, 00M, M1, M2, M3, whatever, and you look at the additional conditions that you get from that, for 3 it's still okay. For 4, something goes wrong there. Okay? From 4 and up, something goes wrong, and the chance of having an ESS like this goes to 0. That's our conjecture, but again, as I said, from conjecture to proof, there is still a big.
Instead, you just look for symmetric Nash equilibria.
Well, symmetric Nash equilibrium. What's the probability of having a symmetric Nash equilibrium, Yuval? 1. There always is. That's Nash. Nash in his thesis proved already. No, Nash. No, but let me just say for those that you. Sorry, I'm pick on you. I'm sorry. I shouldn't do that. Yeah. So Nash theorem says in an n-person game, finite, there is always a Nash equilibrium. If the game is symmetric, there is a symmetric Nash equilibrium. Just apply the fixed point to a symmetric function, and that's it. So there is always a symmetric Nash. There is no problem. The question is so the problem is exactly that the immune to the stability, the immune to mutation.
The question is all this further information. So the probability there is a symmetric Nash equilibrium supported on K pure strategies, is it going to Poisson of 1 over K? And can you add the first K to get, or I mean, maybe it's not 1 over K because.
No, on this, okay, those things are known. Okay, I have to ask my co-author Yossi, he knows on this. He has some papers exactly on this. These things are well known, which means I don't know exactly what they are, but they are well known. So not by me at this moment, but yes, I can give you a reference exactly.
In the case of 2, there was just a factor of 2.
Yeah, right. And
that, so one was new and the other was known already. So except for this flip, everything was.
Oh, by the way, when you talk about Nash equilibria, there is some nice work of Barani and some other people that have a nice algorithm for computing Nash equilibria in random games. Okay, where also they get to exactly this kind of geometric figures, which is faces in d-dimensional space or k-dimensional space and all these things. So this connection is being explored. I can't say whether it has reached its conclusion or not, but I can give you the reference to Barani's paper. Yes, in fact, he's going to be in Jerusalem next month, so we have to to talk about all these things. Okay. Now let me give you a few more open problems. Good, right? I said 1 hour, so okay. So that's just, well, one thing is that we have defined the class of exponential and faster Okay, as those things where you take exponential and apply a convex transformation to it, essentially, or if you want that the tail is a log I never remember. Okay, the tail is, so it's e to the minus x squared, so log concave. Okay, it's a log concave function. Okay, in fact, could be much larger. In fact, turns out that the only thing that you need is that, sorry, that should be lambda n, that the expected number of vertices should go to infinity. So anytime you have a distribution for which you can prove that the expected number of vertices goes to infinity, then everything then is going to behave exactly like the exponential and faster. So in particular, there are lots of other conditions that will guarantee you that enlarge this class. Okay. Another thing, some open problem. Suppose you have bounded support. So, but 0, 1, but it's not a uniform distribution, but it's a distribution that goes something like this, with very sharp tail, okay? Or maybe it goes and starts wiggling around, okay? What's going to happen? Okay, we don't know. My co-author conjectures that it's still going to go to infinity, but it's an open problem, I don't know. So even if you take a bounded distribution, but not necessarily log concave or something that goes neatly like this, but suppose it starts jumping like this, does it go to infinity? The conjecture that it probably does, but maybe at a much lower rate. So Benji thinks he has an example of square root log log n or some, or log 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 n or something, but one gets into uncharted territory there. Okay, what happens with finite support also? Suppose you have distributions finite support, okay, but not finite support. Sorry, I meant discrete support, discrete countable support. Yes, okay. Again, not no. Who was supposed to remember a question? I don't remember. Okay, you, somebody. Okay, so
You have to log symmetry.
no. Never mind. I'll give you an answer. I have an answer. Well, I forget the question. I have an answer. Okay. So what we show, yeah. So we show distributions for which the limit is infinite. We show distribution where the limit is 4. Let's go back to the number of vertices. Okay. Can you have a distribution where the limit is 17? Sure. Because what happens for every n, fix n now. Okay. When you fix n and you ask how many vertices there are for the problem when you have n points. Well, that depends on a certain portion of the tail of the distribution, which is around the 1 over n point. Okay, so essentially what happens? Okay, so if this is your distribution, okay, you take here a point where this mass here is 1 over n, and more or less some neighborhood of that. That's what matters, because if you have n points, the probability of getting points much further away here is very small. And since you are talking about extreme points, maxima, you want to be in that region. So that's the region that matters. So once we understand that, again, that doesn't mean that I can tell you exactly what the neighborhood should be, but roughly speaking, I can start gluing tails. I can take a tail, a normal tail, and glue to it a tiger tail. Sorry, I mean a Cauchy tail, yes. I can start, yes. Nobody says that it has to go down monotonically, concavely, or convexly, and so on. I can take for certain n tail that looks exponential, for a much larger n tail that looks like Cauchy, and so on. Then I can get different limit points, in principle, yes. So those results are for distributions that behave nicely, like e to the minus x to the alpha for various powers of alpha, or polynomial in x, or things of this sort. But if distributions start jumping around, I can probably, again, that's conjecture, but I think one can sort of see how to start gluing those things. I mean, maybe painful, but in principle doable. Okay. Also, remember, we only talked about Poisson distribution for ESS. For this, I don't know. It's a different problem. Okay. In fact, maybe Barani knows. I mean, what happens there. Okay. And I think that's it. Yeah.